there it goes. So if there are no further questions, so this leads us to the talk of Professor Assaad on Fermion Monte Carlo, the auxiliary field determinantal approach. And he wanted this session to be particularly interactive. He finds it boring to sit in front of a screen. So if you have any questions, do not hesitate to interrupt us. I will try my best to collect the questions and forward them to Professor Assaad, and so that we can have a discussion and so that he doesn't feel bored. So, so now we'll have the talk by Professor Assaad.
So hello. I think you can see my screen, I suppose. Let me organize myself a bit before I start. Here it is. So welcome to this talk on Fermion Monte Carlo. As Florian said, if you have a question, raise your hand, you can interrupt, and let's make this as interactive as possible, okay? That would be very nice. So I think everything is on, I can start. So there are many references for Fermion Monte Carlo. We have a review, an old review with Hans-Gert Everts, which we wrote really some time ago. And then there is the first documentation for the ALF, which is sort of halfway between documentation and also some information on the Fermion Monte Carlo. And this has now been upgraded to this ALF 2.0, where we have actually much more physics and much more details on how the auxiliary field Monte Carlo works. Of course, the emphasis is on the implementation. Okay, so let me start with why care about Fermion Monte Carlo. And so this is a list of things you can do with this code. You can look at Fermion quantum criticality, so various type of transitions between a semi-metal and an insulating phase with a broken symmetry. You can look at nematic and ferromagnetic critical points in metallic environments, also antiferromagnetic critical points work also. I see that Sylvain is here. So with Sylvain, we did a lot of condo systems, and we continue with Tarun on this. So you can do a lot of, this is extremely interesting. You have basically metallic surfaces, and on top of these metallic surfaces, you can put magnetic atoms. You can build structures up to, from nanostructures to condo lattices. This can be done. Maybe what we have been doing recently are lattice gauge theories coupled to fermionic matter. So there is a Z2 version of this in the code. There is also, you can do also compact to one and ask yourself the question of, do deconfined phase survive at n equals 2 when you have SU2 spin symmetry, for example? You can do long-range Coulomb interactions in semi-metal, so that is something more realistic. I mean, if you would like to simulate graphene, then you should, in principle, take into account the long-range Coulomb interaction because there is no screening. Electron-phonon problems are possible to simulate, although they're very hard because of sampling issues. So there's still some progress to be there, in my opinion. And the list goes on. SUN quantum antiferromagnets, competition between antiferromagnetism and dimerized states. Various forms of deconfined quantum critical points can be done. Very recently, this is done by a student here, Senju Wang, continuum regularizations of field theories by using a projection to the Landau level. So that's very new and rather interesting. Yukawa, SYK type models have always been introduced and can be simulated also with this auxiliary field. So you can do a lot, right? But you should never forget that it's a balancing act somehow, because all these, if you're not very careful of how to exactly define your model, have to have specific symmetries, then the models will have will suffer from what you call a sign problem. And instead of having a problem which you can solve in polynomial time, then you will actually have a problem which becomes of exponential complexity. So you have to be very careful of how you formulate your problem so as to be sure that there is no sign problem and that the whole code can work. Okay, so this is all these points here can be done with our package. And the first question is how to write down a Hamiltonian, which is flexible enough so as to be able to tackle a lot of different model Hamiltonians. So this is what we have. And so there are many terms, right? Actually, not so many, actually 3. What we have is a hopping, which is here. You can see my pointer, I think. Hopping, essentially. So this is a one-body term, as Jefferson was saying. Then the interactions, which are here, they are two-body interactions, and we will always write them as a sum of squares, of perfect squares. And so for the people who know auxiliary field, you see that the perfect squared is very useful because it's very easy to do a Gaussian Hubbard-Statonovich transformation out of this. And then if we want to, this term here, these 2 terms here, is let's assume that we would like to simulate something of fermions coupled to a field. It can be an Ising field, it can be a scalar field. And so we have this possibility. So Z essentially can be a real field or an Ising field. So this field can be coupled here to a one-body term. And the dynamics of this field is given in this H Ising. So Ising is historical because in the first version of ALF, we had only Z2 variables. Now we can have a scalar observables. So,
Okay.
yes?
Is it possible to change the color of the pointer? Because the pointer right now is showing up in white.
Yes. No, it's not possible. If I can only write on my screen or have something white. So I can use this pointer. Is that better?
I guess it would be.
Okay, so I'll try to prepare this. So this for the Ising term. So to tell you how this works, let me try to start off a bit with symmetries, right? So you see that we have fermion operators here, and these fermion operators have a bunch of indices, and these indices are important because they tell you how we think about implementing the model. So the first index is X, and this will give you the information on the unit cell, I, and on the orbital in the unit cell. So what we normally have in the ALF is that we have translation symmetry in I, that's a Bravais lattice, and so the crystal momentum is corresponding to translations in I, is conserved. So that's the first index, right? Then we have a index which is sigma, which we call a color index. And when you see sigma, only comes in the C daggers and the C's, in the C daggers and the C's, C daggers and the C's here, but they do not come into, they do not play, they do not appear in those matrices, T for the hopping, V for the interaction, and I for the coupling of the scalar field to fermions, which means that we have a symmetry, an SUN color symmetry in this sigma variable. Then we have a variable S, which we call a flavor. And so that's another index, if you want, to the C dagger. And essentially what you will see is that everything is diagonal in S, right? So you have here SS, this is diagonal in S. This is only a function of S, a function of S, not of S and S prime, for example, which means that our system is block diagonal in the spin. So for example, if you take a Hubbard model in a magnetic field in the Z direction, the spin would become a flavor index because the hopping, for example, to account for the Ising term will be block diagonal in S, right? So these are the symmetries we have. So let me talk a bit more about the form of the model. Now we understood the symmetry. T is a hopping matrix, right? So if I take only this would be the hopping matrix here, and I'm allowed to have many of them. So to go a bit ahead, if you want to do a checkerboard decomposition, then you could use this T as basically hopping on a bond, and then you can sum over many bonds. So that's one possibility. V, okay, so that will be, so let me go one step back. T, V, and I, they all have to be Hermitian. So that's something which is very important. That's built into the code. So what we have is that the conditions is that T dagger is equal to T, and then V dagger is equal to V, and then I dagger is equal to I, right? So this, I really need this to implement in the code, okay? So this is, so you have many possible, so this is again, for example, this perfect squared could take care of our Hubbard interactions, and here the K from 1 to MV would sum over all the lattice sites, and U would be the interaction strength, et cetera, et cetera. This Z could be a phonon, which would couple to a kinetic energy, for example. Okay? So I went a bit too fast now. So I have here two body interactions. I already talked about this. The one body term couples to an Ising field or to a bosonic field, as you like it, or scalar. So it has to be a real field. And then the Ising term here gives me the dynamics of the scalar field, essentially, and that has to be implemented also. So the only thing you have to give in for the code, actually, to work is these matrices T's, these matrices V, this shift alpha, this matrix I, and the dynamics of the bosonic or scalar field, plus all these, you know, how many hopping terms do you have, how many interactions terms do you have with the interaction strength, how many of these terms you have, which single body terms, which couple to a scalar field you have, etc. So in principle, if you give this, then the code will run. Questions? So you can raise your hand or not raise your hand if you have questions. I can see your hand raising. Or if there's a problem with the presentation. So this is not the case. So let me go on. The outline of the talk is the following. So these are all the points we will go. We have quite some time. So we'll go through all these points. First, start with, you know, to put everybody on the same page, to just basic Monte Carlo. These are only 3 slides, but I'd like to be sure that we all know how to do that. And then the auxiliary field quantum Monte Carlo. And there are many steps, right? You have to take to be able to implement things efficiently. And actually, all these steps have some type of pitfall. So you have to be, and I'll try to, you know, to make them very clear where the problems are. So we have to do a Trotter decomposition that comes with some issues, maybe sometimes. Hubbard Statonovich, which one should you take? It's not unique. You have then to integrate out the fermions. That's pretty easy. Well, there's no, you can't do any mistake here. Measurements, Vick's theorem. When do you have an absence of sign problem? That's extremely important. And then from 9 onwards, the organization of the codes and fast updates. If we have time, I will talk a bit more about different updating schemes. So we are building this still now in the code, Langevin dynamics and hybrid Monte Carlo. We would like to put in the version 2 of the ALF, at least Langevin dynamics. And then some issues like stabilization, especially for the finite temperature code. And then this will bring me to the different, so the first part is for the finite temperature auxiliary field quantum Monte Carlo code. There are some specializations to projective approach if you're more interested in ground state properties. And then I will give you some examples of how you can do with ALF, what you can do with ALF, some very basic examples. And then at the end, some project suggestions. Of course, you can come with your own project, but some project suggestions of, you know, what you can do during this week to get used to ALF, right? So let me start with the Fermion Monte Carlo. No, with the just Monte Carlo. Essentially, we assume that we have a space omega, right? It can be anything, right? A space omega, and on this space omega, we have elements X, which we call configurations, and each configuration comes with a probability. So P of X is a probability distribution on omega. It's normalized, and because it's a probability distribution, it has to be bigger than 0, right? And the goal is to be able to evaluate expectation values of an operator with respect to this probability distribution. And that's basically the integral over the configuration, the probability of a configuration times the value of the operator or the function for this given configuration. So the Monte Carlo works with the following assumption. Assume that you can generate a series of configuration X of I, which are distributed according to P of X. and that's what comes here is very important, that O of xi are all statistically independent, right? So it is statistically independent of the measurement you do is, of course, extremely important for the Monte Carlo. Otherwise, you will have problems with the error analysis. So if this is satisfied, then you can estimate O of p by a finite sum from I goes 1 to n. These are the number of samples you have of the value of the operator for these given samples. And so I will call this x, big X, which is an estimate of O of p. Now, the question is, what is the error on this x? And we can use the central limit theorem to show that, provided that O of xi are all statistically independent, that p of x has a Gaussian distribution. The width of it is basically the variance of the observable we're calculating. So if the variance of this observable is finite, then you see that the error, we can call this the square of the error scales as 1 over square root of n, the number of samples. Now, what is remarkable for the Monte Carlo method is that this error, the scaling of the error as a function of 1 over the square root of the number of samples, or the CPU time, essentially, is independent on the dimension of the space, right? So you can use this. Monte Carlo is strictly speaking, Monte Carlo is a bad method, but it becomes very attractive when we have very high dimensions, right? So to give you an idea, if I take a Hubbard model on a 16 by 16 lattice, right? And let's say a beta t equals 10, and a finite time step, imaginary time step of 0.1, then I'm at basically Hilbert space of basically, I have 200, essentially this will give me 256, so I can't even read, 25,000 Ising spins. So that will give me a dimension, basically the number of configurations I have is basically 2 to the 5, 600. That's typically what you will do with the ALF. And out of this, out of this huge space, you get away, this is a huge number of configurations. You will get away with, let's say, 10,000 to maybe 100,000 configurations will be enough to give you a good answer. So that is pretty remarkable. And at the same time, it's a bit scary because you have to choose these very well, and things can go wrong. So you have to be aware that you sample an extremely small fraction of the configurations, hoping that some of them, only part of them will be very important, and you can forget about the rest. Of course, this is controlled, right? So how do you go about generating this this series of configurations? Well, we need some type of transition probability, T of x to y. So I read this as the probability of going from configuration x to configuration y. This is a matrix which has to be normalized to unity, which means that if I am in configuration x, the probability of going to any other configuration y is 1. It's again a probability distribution, so it has to be bigger than 0. All the elements of this matrix have to be bigger than 0. So what do we need? What do we require for this matrix? Well, we require that it's, first of all, ergodic, right? So for any 2 points or 2 configurations, x and y, there exists an s, right? So that if I elevate t to the power s, then there is a path that is bigger than 0. That means that there is a path between x and y. What we require also is stationarity. That means that if I am, what the Monte Carlo does is essentially to evolve some type of distribution, if you want. So if I've evolved distribution, so this is the distribution I would like to sample, P of x. If I've evolved it with the transition probability matrix, then if I am in equilibrium, then I stay in equilibrium. So this is called stationarity, and this is the most important thing you need. You actually don't need detailed balance. So detailed balance would be something like this. Detailed balance would be, let me put in a unity here. So that would be, if I put in the sum of all the y's and then a t to the y x, because this is a normalized matrix, this is only a 1, that does not mean, from this does not follow the detailed balance condition, basically d of y x, p of x is equal to p of y, t of yx, right? So this is detailed balance. Detailed balance, if you have it, good, then you have stationarity. But if you have stationarity, you don't have detailed balance. And in fact, the algorithm, the ALF, is a single spin flip sequential updating scheme, satisfies stationarity, but does not satisfy detailed balance, but that's still perfectly okay. So if you have these two cases, these two things, right, 1 and 2, then you will get the result in the following way. If I start with any configuration x1, right, the result should be independent of the starting point, and I iterate, right, this matrix t times, right, and then after iterating t times and taking, you know, t going to, I mean, summing up everything to doing that for a very long time and dividing by n, then basically what this equation is telling you is that if you iterate your Monte Carlo a lot, then the fraction of the time in the sequence of configurations you have, the fraction of the time you are in configuration x is given by this probability distribution p of x. Okay, so you can sum up over all these time series and then essentially of this over this time series, and then essentially calculate, you will have p of x. Okay, so that's how it works. How do I define my t of yx? I will only give you the result here. What I need is to define a set of rules, right? So these set of rules are your choice, and if you're clever, then the program will be good. If you're not, the program will be slow. And then if I give you these choices, I will assume that I will never propose to stay in a given configuration. Then t of yx is given by this. The proposal, so to go from x to y, I will propose a move from x to y, and I will accept it with this probability distribution. But I will also have to take into account that I may stay in the configuration x if I propose a move from x to any other z, but I refuse the move. So that's basically the probability of staying at position y. Now, if you take a of yx as this form, this is called the Metropolis Hastings acceptance rejection form, then you are sure that this, out of this given rule, which you take, which you devise, then this probability t of x to y will have the desired effect, and that will actually help you to sample the probability distribution p of x. Okay, so I'd like to, I think I will not spend too much time on this case, but just to tell you, you should be very careful with Monte Carlo. Monte Carlo doesn't have to, but it can go wrong. And you should always check your results against exact answers on small lattices. One thing you can do, which is done here, and many references, you can just take a one-dimensional Ising model and do your Monte Carlo, do the Monte Carlo run, and you will see. So Florian is telling me that the pointer is not visible. Florian, is that still okay? No, that's okay now, I hope.
You found a way.
You found a way, so that's okay. So just check your results against exact results and do a small exercise of the one-dimensional Ising model. It's easy to program, and you have an exact result with the transfer matrix, which you can easily calculate. Okay, and in the section 4.2 of the ALF documentation, there's a very detailed guide of how to do the error analysis, and please take a look at this because that is important. So now let me go on to the auxiliary field, Monte Carlo. Here it is. And so what we do in auxiliary field is equilibrium thermodynamics, and the quantity, the most important quantity is the partition function, and we will write the partition function. So this is a many-body Hamiltonian, which is complicated, and what we will do is to make it simple by, or simpler by introducing a field phi, which has a space and time dependent, and for each of these fields, right, we will have we can define an action S, which depends on the field. And this action has to be easy in the sense that it's a one-body problem in an external field. So if you give me the field phi, then I can calculate this action in polynomial time. What I cannot do in polynomial time is to do the integration right over this field, and this will be done with Monte Carlo. And you see right away that this can only work if this action is real. If their action becomes complex, then you will have, as is generically the case in path integrals, if you have a topological term, it will be complex, right? So this can become complex, and that's where the sign problem comes in. We'll talk more about this afterwards. So I'd like to go through this program based on a very simple example. So I'll take back simple. This is not so simple. It's a one hopping, right? This could be hopping on honeycomb lattice, for example, one body term. And this is a generic long range, a two body interaction. So that'd be the Coulomb interaction. And we will go through, or the specialist can see that this would be the action right away, but we will go systematically through all the steps required to show that the action is actually given by e to the s is given by this expression. So we'll go through this. This Hamiltonian here, single body term and long range interaction, is actually in the ALF. So if you go to the as one of the example Hamiltonians, so it's called Hamiltonian long range Coulomb mod .f90, and there's also a Python script which will allow you to run it. The method we will present here has a very long history. It was started off in the high-energy community by David Scheich, Pete Brower, and Claudio Rebi. Maxime, who is now also in Würzburg, picked it up and did some hybrid Monte Carlo with this. Then we continued with some auxiliary field Monte Carlo, et cetera, et cetera. And it's one very nice method to tackle long-range Coulomb repulsions. So how do we formulate this, and how does it work? And the first point is the Trotter decomposition, right? If what we have to do is we have to isolate, to do the Hubbard-Statonovich transformation, we have to isolate the interaction term from the hopping, right? These two things don't commute, and so we have to do an approximation. The Trotter approximation is like this. The simplest form is that if I have the partition function here, z, then I will approximate this instead of having, so there's a set of infinitesimal time evolutions, and I will first propagate in imaginary time with the hopping, propagate in imaginary time with the interaction, and iterate time, this time L tau time. So this is number of Trotter slices. And we want, of course, that L tau times delta tau is equal to beta. So this comes with a systematic error, which is of the order delta tau v squared, right? And so is that bad or not bad? Can you cope with this or not cope with this? And so this has become more and more important with time, in my opinion. And there are things you have to be very aware of what can go wrong with the Trotter. If you use this Trotter decomposition, which is not symmetric, then you can show that you see right away that E of H1, E of H2 is not a Hermitian operator. So if you want to write it down, it will be E of minus H3 plus an imaginary part H4, right? And so, you can go into this. There's a beautiful reference which will give you the full corrections to the Trotter decomposition, etc. It's very nice. And you'll see that this H4 here has this form, right? So if H1 and H2 don't commute, then you could really have an imaginary part. So if you take this Trotter decomposition, then suddenly your propagator, which you have, violates one of the basic symmetries. It's not Hermitian, right? So it could have an imaginary part, and the eigenvalues would have some imaginary part, and in imaginary time, you would start seeing some oscillations in imaginary time displays Green's function. I'll show you this afterwards. And so one possible remedy is to go to higher order Trotter decompositions and to do symmetric ones. And this is included in the ALF. We can always do a symmetric Trotter decomposition so as to avoid this problem. So let me show you one of the things which you don't want to see. But this is, let me do this bigger so that I can see it, right? This is a 6x6 a honeycomb lattice Hubbard model on at u over t equals 4, beta t equals 4t. And what we're measuring here is basically the Green's function. So at r equals 0 at tau, and then c of r at tau 0. Okay. And now what you see, this is the tau axis here. This is the quantity. And then if I use a symmetric, not a symmetric, so this is sim. Sim is a variable in the ALF which tell you if sim is true or yes, then we use a symmetric Trotter decomposition. If sim is n, then we use the asymmetric Trotter decomposition. And you will see that this is for the asymmetric Trotter decomposition. What happens is that I get a 0 in this quantity. This quantity has to be definite, positive definite if my Hamiltonian is Hermitian, and you see some zeros which pop in. If you go to smaller values of delta tau, then these zeros are pushed off if you want to lower scales, but they're still present. And the way to get rid of that is to use a symmetric. So you have this flag sim equals yes in the code. If you put sim equals yes, you have a symmetric Trotter decomposition, and you see that this is the result here for the symmetric Trotter decomposition is perfectly okay, and it does not depend on the delta tau error. So this is one example where be careful with the Trotter. Always try to do symmetric Trotter decompositions. If you don't, then you can run into some pitfalls. Okay. What is the prefactor of the error? How does it scale with system size? So you can take the symmetric decomposition, right, and ask yourself the question, well, this is my approximate free energy density. And if I do a bit of algebra, then my approximate free energy density is equal to my free energy density, and then this correction factor. So this is a commutator of a commutator. And you should ask yourself the question, well, how does this commutator of commutator scale with system size? If you have HV and H0, which are sum of local terms, then you can argue that this will be proportional to the volume. This commutator will be proportional to the volume. The commutator of the commutator will also be proportional to the volume. So I have a volume term here, which cancels this volume term here. And the systematic error will be of the order delta tau squared, independent of volume. Right? So that's okay. You can make your system size bigger and bigger, and you don't have to make your Trotter smaller and smaller. So Senju Wang encountered a case where this is not the case when you have non-local Hamiltonians. This is what happens. So this is, I won't talk about this, very nice article by Senju. And essentially, in this case, it can be that this scales as the volume, so that the whole thing scales here as the volume to the cubed, right? This is like volume times volume times volume, volume to the cubed. You divide by the volume, so you have 1 over volume squared. And you see that for some Hamiltonians, which are non-local, then the Trotter has to scale as 1 over the volume to be able to keep an accuracy constant as a function of the system size. So that is a problem, right? So this you have to be very careful about this. And we're still learning the problems of the Trotter. So many other problems. If you're looking at critical phenomena, does the Trotter error introduce a relevant operator? If it, for example, it could break SU2 spin symmetry, the Trotter decomposition. And then you will have to be sure that you break a bit the symmetry, but you have to keep this very small so as to be sure that your RG flow does not flow away, right? So you have to be very careful about this. There is the possibility of, there are some methods to get rid of the Trotter decomposition by using, I think it's more restricted for a class of systems. So you can talk to Emily Huffman about this. And I think that it's not as general as what we can do with the Trotter. And then finally, if you're interested in higher order methods, then you can ask our chairman. He has been working a lot on these Trotter decompositions. So you see just the time we take for Trotter, you may say it's a detail. It is a detail, but once you really want to get results, you have to be a bit careful about the Trotter decomposition. Okay. So I spent enough time on Trotter. Now let's go to the Hubbard-Statonovich transformation. Now, the Hubbard-Statonovich transformation, the idea is how should we basically split a two-body interaction into a sum over many one-body interactions. Essentially, this is just a Gaussian integration, right? So so this would be for the long range Coulomb that you can show. We won't have time to do this all together, but if you ask me some notes, I can put up some notes to show you how this works. Essentially, what you can see is that you can go into a basis where this is diagonal, then do a Gaussian integration, and then you will see that this quantity, basically V of ij density-density interaction, is equal to the integral over your field. This Gaussian term, you get a V of -1 of ij with a minus in front, and that's where you see that for this to hold, V has to be positive definite, right? So that this is well defined. Otherwise, if V is negative definite or positive semi-definite, then you have zeros and everything will diverge. And this field couples to the density of electrons minus a background, which is 1. Right? This 1 is important, and it has here an I in front. So if you care to do this integration, it's not very hard to do. It's a Gaussian integration. You will go back exactly to this. What we generically have in the ALF is the following: is that we approximate the Gaussian integration by this form, right? So we already have. So what this is E minus delta tau of an operator to the squared, and I will write this as a form with L plus or minus 1 plus or minus 2, gamma L, this is a positive number, which is listed here, and E of the square root of delta tau, a field eta of L, right? Eta of L is odd, for L goes to minus L, which couples to A. So this is actually not exact. It's exact only to delta tau to the 4th. But since we already have an error which is proportional to delta tau to the squared, this is because of the Trotter decomposition, this is as good as exact. The big advantage of this is that you have now a discrete variable as opposed to a continuous variable over which you have to run the Monte Carlo, and this makes, in many cases, makes life much, much easier. So this essentially is the formula we use to decompose all of the perfect squared terms in the ALF, right? So that's very general. This is nothing but the Gauss-Hamid quadrature at n equals 4, so you can go to Wikipedia and see this, and also talk to Florian about this. He has been working a lot on these aspects also, and how to go to higher orders. So we're stuck with perfect squared, and the question will be, is a perfect squared general or not general? And it turns out that it's pretty okay. You can do a lot of things with perfect squared. These are the canonical example. A Hubbard interaction, here it is, can be written as the squared of the magnetization in z direction. It can be written as the squared of the density fluctuations. If you were interested in a nearest neighbor interaction term between two sites for spinless fermions, you can write this very compactly as the hopping to the squared. This is only for spinless fermions, right? Et cetera, et cetera. And you can go on, right? So I will this is just a slide to show off essentially what you can do with perfect squared. So this is a model we've been working on with Toshiro and Tarun, and what you can this is a generic spin system, right? So we can simulate this for any values of JZs, right? JZ of ij can be any number. This is a spin on any lattice, right? A spin system on any graph or any lattice. J-perp has to be smaller than 0, right? So this is a spin system. Here I have a fermionic system, which is just a repulsive Hubbard model on a given lattice. And the conditions for the absence of sign problem is that T of xy that you can divide the lattice into 2 sublattices, and that T of xy only talks between sublattice A and B. And then you have here a complicated, it's a bit modified Kondo coupling term between the conduction electrons, here are the C's, and the spins. And this -1 to the x, which is a sign which depends on the sublattice, is there to be sure that we can avoid the sign problem on any lattice. So we can simulate this, and you should just, if you go to the supplemental of this paper, then essentially what goes into the code is this Hamiltonian, right? And you can show that this Hamiltonian, so this is in a Bogoliubov basis, you have an F tilde, which is given by this, basically a particle hole transformation in one sector. We fermionize the spins. The spins are written in terms of fermion. We impose the constraint by adding a Hubbard U here on the F's. And so if you can rewrite your Hamiltonian in this form as a sum of perfect squared and put it in the ALF and rather efficiently, simulate a very generic Hamiltonian of spin 1/2 coupled to fermions. So that's essentially all the physics of heavy fermions.
Fakher, there's a question in the chat.
Yes, please.
By Nicholas Kowalski. Do you want to?
Yeah, so he can unmute his speaker and ask.
Right.
That'll be okay. Hello.
Go ahead. You're unmuted, Nicholas.
Do you hear me?
Yes, I can hear you very well.
Is it better now? Okay. What you said about the sign problem, is it if you have two sublattices A and B between the lattices or inside the lattices in order not to have a sign problem?
So you have to, you just take a graph and you have to be able to split your graph in two parts, A and B, right?
Yes.
And then the rule is that you have to have hopping only between A and B. There's only a connection between A and B. That's
not between A and A or B and B. Okay.
No, if you have A and A, that would be like a chemical potential, and that would be a problem, right? That would dope with it.
All right.
Okay, we'll come to
Very
this.
much. Yes. Thank you.
So, thank you. Another question? Well, thank you for the question. I'm happy to see that there's still somebody listening. And so let me go on. So now essentially with the Trotter decomposition and the Hubbard Statonovich, we came to our problem here of long-range Coulomb. So this equation now should be clear. We have on every time slice we have to do a Hubbard Statonovich decomposition. So this is this field which is now a sum of I and tau. It depends on position and space. This is the hopping, and this is basically what comes from the Gaussian integration. And then for the notation, it's easier to write everything in this way. The hopping here, H0 will be essentially H0 will be written like this, right? This is H0, and then the HV essentially here. This is a diagonal term, right? This one here will go into here. This -1, which is very important, will go into the action here, and I'll combine it with this to get this S0. Okay, so if you forget this one here, then you will get a sign problem. If you get a +1, you will all get sign problem. So you have to be very careful. So this is how we will write it, and we'll define these matrices V and this matrix T, right? And what I will also define, or what in the original papers of Calipino and Blackenbeckler and Sugar, those B matrices which are dependent on phi of tau, which is basically the exponential of minus delta tau, the hopping, and exponential of minus delta tau V, that's the interaction matrix, which I can read off directly from here. So I will need these two things for after. Okay, so this is the formulation, and now we have to go on, and integrate out the fermions. So integrating out the fermions is rather technical, here there are many ways of doing it, but the most elegant way to do it is for you to go and pick up, for example, the Nageli-Orlon and read about coherent state path integrals. Because if you have this, then everything becomes very, very easy to compute, and you can see things rather easily and where the structure comes from. So so these are, of course, I cannot go through the Nageli-Orlon now, but these are the points. A fermion coherent state is an eigenvector of the destruction operator, right? Psi cannot be a real number, that won't work. It has to be a Grassmann number. The Grassmann numbers, they anti-commute. So this number is or dagger or nothing. They anti-commute between themselves, these Grassmann numbers, and they anti-commute also with the creation or destruction operators, okay? So the states, I can write them this way. So for example, we can do this one, we can do it for one mode. If I take, for example, I just take one mode, if I take C of, let me do this a bit bigger, let's see if I can do this, of psi. If I just take it for one mode, that's basically C of 1 minus psi, and then C dagger. I just take one mode, so I'm forgetting the X on 0. Now, if I just pass this through, the C on 0 is 0. The C anti-commutes with the psi, so I will get a plus psi and then a C dagger on 0. C dagger C on 0 is basically 1, so I will get something like psi on 0, and then I can build it up again like C. Sorry, this is wrong. Like psi of 1 minus psi C dagger of 0, and that's an identity because psi squared, because of this anti-commutation, psi squared is equal to 0. So you see that this form, you do it for all the modes, for all the X, but basically this form exactly tells you that this is an eigenstate of the destruction operator. And then you can go on, right? This is, if you just take one mode, for example, it's rather easy to show that essentially if I take psi prime, that would be, so I have to be a bit careful, that would be just for one mode, 1 minus C psi dagger on 0, and then I have this is like this, and then I have a 1 minus psi C dagger here on 0. If you calculate this, then what you will get is basically a 1 psi dagger, this is psi prime here, and then because psi dagger to the squared is 1, then that's just equal to E of psi dagger psi prime. Okay, so you've shown that the overlap for one simple mode, just for one mode, that the overlap between two Grassmanns really have this form. You can define an integration over Grassmann field, and basically how should we define this? Why is it so that d of psi over 1 is equal to 0 and d of psi is equal to 1? Well, one thing you would like to have is that if I have a function of my Grassmann variables and I shift it by a real number a, then this has to be equal to integral over d psi of f of psi, right? And so if I want this, then it follows that I should define this integration over Grassmann variables this way. So et cetera, it's a fun algebra, very nice and very useful algebra to play with, and you should read the Negri-Orlan, which is a beautiful book for this. I'll go on. You can go on. Resolution of unity. So this is I'll just give you this as a formula which you can find in the Negri-Orlan book. And what is also important is the trace over the Fock space over an operator A, and that's the integration over Grassmann variables. You have this factor psi dagger psi. And importantly, you need a minus here, A and psi. And this minus here, this is what gives you the anti-periodic boundary conditions in imaginary time, and essentially defines fermionic Matsubara frequencies, which are 2n+1 pi divided by beta. Okay? So once we have these things in the box, this is standard, right? This is standard Negri-Orlan many-body physics. Then we can go about and use it for this to evaluate this trace. And so this trace here is the product of one-body operators. And to make our life easy, I will approximate this. You don't have to do this by 1 minus delta tau and then C dagger VC plus C dagger TC, okay? Right, plus O of delta tau squared. That makes it easier for us to do now. And then at each time slice, right, each time slice here, you will insert the resolution of the unity, and you will use this formula to get the trace. So we can read off what will happen. Now, the expectation value of this here comes in here, minus delta tau, because I will re-exponentiate it. I have 1 minus delta tau. So I get my delta tau here of h, which is now defined exactly like this, but now with the Grassmann variables, tau on one side, tau plus 1 on the other side. This here comes from the resolution of unity. This is this term here. And this term here comes from the overlap from this equation here. Okay? And importantly, what you need is if I go from tau of L tau plus 1, right? Then this is antisymmetric. It's equal to psi dagger of x at time slice 1, but with this minus, and this minus comes exactly from this trace of formula. Okay, so that's the form to do it. If you want to do things a bit better, right? You can note that you don't have to. So we did an approximation here, was to use this expansion. You can do things a bit better by noting that if I want to this thing here, e to the c dagger ac, what I have is basically given by the normal order form of this. And once you have something which is normal ordered, then you can replace the c daggers by the xi's right away, and you don't have to do this approximation. This is maybe more advanced, and we don't need this here. So the second step is, the next step is the following. Well, now I have I can define a matrix. So I took this from the other place, right, from the other slide, and I can define a matrix, psi dagger of alpha. Alpha is now a space-time index, and a big matrix, which has a space-time index, psi beta, and we can read it off here, right? So for example, I have a minus here. So the 1 is essentially comes from this term, psi dagger psi, which is equal in space and in time. So this gives me my 1, which goes over the whole diagonal. Then I have something which is a tau plus 1 tau, which comes with a plus. But since I have a minus here, it comes with a minus. This gives me always a 1 in, let's say this is tau plus 1 is equal to 2 here, and tau is equal to 1, right? So this is 2, 1 position. And I have the same thing. I have also the Hamiltonian, right, which comes from here with a minus delta tau, but I have a minus here, so it's a plus delta tau, and this t plus v, which I write here. And then at this point here, instead of having, I have to take into account the anti-periodic boundary conditions for the size. So I have exactly the same thing here, but now at the last time slice, and I have a plus 1 and a minus 1 here. Okay, so how do we go on? Well, so we go on by picking up the Nagel-Hollande book again and looking at this, demonstrating this determinant formula, that if I integrate over my Grassmann variable of exponential of this object, and I get the determinant of m, right? So we can do this, and we'll get a determinant of m. Before doing it, let me, go back to the exponentiated form. This 1 minus 1 plus delta tau t plus v is essentially nothing but a minus e of minus delta tau phi of n, e of minus delta tau t, and there's an error of order delta tau squared. And this is nothing but my object b of phi n, which I defined a couple of slides ago. And that's still, I'm making an error of order delta tau squared. And for these purposes, this is as good as we need it for the moment. So then we have this form, right? So now we came here. This trace, right, over the Fock space is now given by this determinant of this huge matrix. So don't forget, this is a matrix which has volume times volume. This index is basically imaginary time, right? So we have volume times imaginary times, volume times imaginary time index. And this is a form which you can use for hybrid Monte Carlo, for example, for many things. But for the purpose of for us, what we need is something else. And we have to reduce this determinant to something more tractable to be sure that we are able to simulate our model within, complexity imaginary time, so beta times the volume to the cubed. And to do this, we use this Shor's identity. And the idea here is to, well, just use this, right? Just use this identity. And what we will define is, so let me get this right. This will be A. This will be the matrix A. This will be the matrix B. This will be the matrix C. And this will be my matrix D, right? So now I have these 4 matrices, and I can use the Shor's identity. So what I will get is, I will use this. So the det of D, that's 1, so I can forget about this. Then I have the det of A. Well, det of A is this one, so I find it again here with the 1 here at the end. There's a 1 which comes in here in A. And then if I calculate B, D minus 1 is 1, B times C, then I get exactly this point, this thing here that comes from this term here. So you see that I can iteratively, so the matrix has become smaller actually, right? And I can iteratively continue and, you know, continue, and then at the next step, I will take, this is A. I'll take at the next step, this is A, this is C, my D always stays 1, and this will be my, this is becoming a bit messy, right? But my B, and I can iterate this, and essentially it'll become smaller and smaller, and I will accumulate those B matrices. And at the end of the day, if you do this, the number of Trotter times, slice time, then you will get this, this formula, which is the core formula for the determinant formula of the BSS. Okay, so this is an elegant way of showing it, and it can be done without any approximations if you take care a bit about normal ordering of exponential of single particle operators. Good. So now we're done. We can formulate our partition function in different ways, right? That's actually pretty interesting. We can, one thing we can do, I'll put in my S0 back in. This Z, the partition function, is integral over all my fields phi, right? And I have my bare action as 0, which we discussed yesterday, previously, and then the determinant over all these B matrices. This is the basis of the finite temperature code, and also the basis of the projective code. And if you take this formulation, well, it's really nice because they, you know, if you want to calculate this determinant, for example, then you need L tau, so the number of Trotter slices times a V to the cubed, so it's pretty quick. And you know, you can go to bigger, pretty big systems. To my knowledge, the record is by Seki-san. I think he signed up for this workshop, which is 74 times 74 times 2 electrons. So this is pretty big, around 11,000 electrons. This, I think it was for honeycomb lattice at rather weak coupling, right? So that when you say this is a big lattice, you always have to say what is the system, and you know the system should work rather well. Then another possibility is not to reduce to keep this big matrix. And this is a basis of an old algorithm, which goes under the name Hirsch-Phi, impurity type algorithms, which have been now superseded by continuous time algorithms, which work much better. So I won't talk too much about this. But then this big matrix also is also the basis of another way of doing the Monte Carlo, and that is essentially what people call the hybrid Monte Carlo. The question, which is used in high energy physics, and it's used in high energy physics because in lattice gauge theories, because they are not satisfied with 1 and 2D. They're really working in 3 spatial dimensions plus 1 and 4 dimensions. And so this type of scaling, volume to the cube times beta, or number of Trotter slices, if you go to higher dimensions, is not very good, right? So the bottleneck of this, of course, is the determinant. And what the hybrid Monte Carlo people do is to say, well, you know, let's throw in some new variables, which are called pseudo fermions. These are those phi t's, such as we can stochastically sample the determinant, right? So we throw in some new pseudo fermions, they call that, and you can stochastically sample the determinant. And the hope is you can formulate a beautiful algorithm, which goes under the name hybrid Monte Carlo, where the scaling is in principle better than the ALF or the BSS type algorithms we use. This is the case in some cases, but it's not generically the case. And Maxime, who is in Würzburg, I think holds a record using this hybrid Monte Carlo. He can go up to 102 times 102 times 2. So this is 20,000, 21,000 particles on a honeycomb lattice, again, with long-range Coulomb interactions deep in the metallic phase. So when it works, it's harder to use, it's more tricky, it can break down more quickly than this algorithm, but when it works, it's pretty amazing, okay? So what we will do is essentially stick with this formula, but there are many different ways of formulating it, and this allows you to formulate the Monte Carlo in different ways. Good. So let me go on with measurements. We formulated everything in a form which we can, in principle, sample. Now we would like to measure things. So here it is. So if I retrace my steps, and I would like to, this is what I would like to calculate, right? If we do the Hubbard Statonovich transformation, the Trotter decomposition, etc., I will have on the nominator exactly the same thing as before, but with my observable here, and denominator, that's the partition function which we talked about up to now. Now, to measure things, I will assume that this trace here, which is the determinant, is not equal to 0, and then I can multiply and divide by the trace. And once I've done this, so this is an assumption. This could go to 0. There are some, we know that, there are some configurations where it can go to 0. The configurations where they go to 0 are not so, have a very low weight, because it's 0. But nevertheless, this could, and that has been discussed in this paper, this could lead to problems. Okay, but this is another subject. So once we have this, then we can do the following. Well, this will be now this is the probability distribution I will use to sample, right? This will be my P of a given, for a given phi, right? And this will be this object here. This will be now my observable, right? Which I write with 2 brackets, which is dependent on the field phi. Okay, so this is what we will do. And so this is done on the next page. So this is exactly what I did here. This is my probability, this is the integration over all the fields. This is my probability distribution, P of phi. I'm forgetting about the sign problem. I'm saying that there is no sign problem for the moment. And this is the expectation value of this operator for a given configuration phi. And so you see, now we've come to basically back to the first slide where we have formulated everything with as is okay now to evaluate this integral with Monte Carlo, right? With just classical Monte Carlo. Good. Now, how do we evaluate this, right? How do we evaluate this quantity? And for this, we have to go back to the Legge-Orlan, and this is the fixed theorem. Good. So how do I want to write an observable? Okay. I'd like to define time ordering with respect to my imaginary time evolution. So here I have my imaginary time evolution. If I multiply tau from tau 1 plus 1 to tau 2, and I do these are basically operators which give me my imaginary time propagation, then I will call this a propagator U hat, which is dependent on the field from tau 1 to tau 2. That is if tau 1 is bigger, tau 2 is bigger than that tau 1. And conversely, if tau 2 is, or if tau 1 is bigger than tau 2, then that will be -1, the propagator from tau 1 to tau 2. Okay, from tau 2 to tau 1. Now, once I've defined my time evolution, then the operators I'm interested in can always be written as, so if I organize my time as a time ordering. So time ordering means that the smallest times goes to the right, to the right, and the biggest times to the left. The time ordering of these operators, which I write in this form. So C dagger, position x1, time tau 1, x1 prime, tau 1 prime, x2 prime, tau prime 2, etc., to an xn, tau n, xn prime, tau n prime. Okay, and again, this the Heisenberg representation for those C's is given by this. Okay, so once I've defined this operator in this form, I can go back to my Legge-Orlan, work a bit, and do exactly the same thing as I did before for the coherent state path integral, and I will see that because of the time ordering which I introduced here, that this is essentially just the integration of over my Pythagoras and my Grassmann fields, this matrix M, which we talked about before, so that will be the inverse propagator, and all these psi's here, which are these indices here, are exactly the ones which you find here, right? X1, X1 prime, tau 1 prime, etc. This integration can be done, right? In the Negri-Orlan again, sorry to this I can't do now online, but then what you will have is a determinant of essentially the matrix M of 1, where the entries are M minus 1 between time x1 tau 1 and x1 prime tau 1 prime. And this M minus 1 is nothing but the Green's function, the propagator, the single particle Green's function. So you see that if I know this, right? If I know this quantity, if I'm able to calculate this quantity for a given phi, right? And I'll show you how to do that afterward. Then we can estimate any observable for a given field configuration using this Wick's decomposition. Okay, so that's very important. So the only thing I need is the single particle Green's function. So we can calculate the single particle Green's function. And the single particle Green's function is given by this, right? So it's the M minus 1 is given by this object. You can see this very quickly by just doing the calculation just for doing this calculation here for n equals 1, right? If you do the calculation for n equals 1, then you show right away that this M minus 1, the determinant is only for one entry, that this M minus 1 is just the Green's function. So we would have to, one of the basic quantities in the code is what we call the equal time Green's function on a given time slice, right? And we can calculate this, and we can, so this is the Green's function on a given, so if I will, time ordering here is a bit tricky, but so essentially the time ordering means that here, if at equal times means that I don't do anything in this case, so it's C dagger. And you can show that this object is given by this expression, and so the best thing we can do it if you want. So I can give you some ideas on how to do it. If I maybe I will not have forgotten how to do this, but essentially what I would like to calculate is the trace of the evolution from beta to tau. I'm just taking the equal time C of x, and I'll take a C dagger of y. So I'm changing a bit the indices, U of tau to 0, right? Divided by the trace of U hat of beta 0. That's what I would like to do. Now, the way to do that, that's for a given field configuration. The way to do that is to introduce, so I will take this, I will just commute those two things. So I will have a delta xy, and then what I will have is a minus, and then I will actually put in a source term, do d of a d of eta, and then I'll do this a bit smaller, so I have to write a bit smaller, the log of the trace, of u of beta tau, and then e of eta, and then c dagger of y, c of x, and then u, of tau 0, right? And I have to take this, let me do this a bit nicer, push this that way, here, and I will put this at eta equals 0. Okay, so now what you can do, I won't continue. This is the only trick you need, because now these are the trace. If you take this and you take then eta equals 0, then you can use the determinant formula to evaluate this. You get rid of your operators, you get your determinants, etc., and then you will come to exactly this form here, right? So that's the key step. The key step is to put a source term and then do a logarithmic. You just derive this log with respect to the source term, and then put the source term to 0, and then you're done. Okay, so that's the way to do it. Good. So you can do this at home if you want. And then we're finished essentially. The Wick's theorem holds for a given configuration, right, of field. So if I have the equal times Green's function, and this is something I can calculate, right? If I have the equal times Green function at a given, for a given field configuration, then I can compute any equal time observable, right, from this Green's function by using just Wick's theorem. Okay. Let me note that there is an extremely elegant way of writing, essentially of reformulating Wick's theorem that was done by Tarun in 2013. And essentially, it elevates this equation, or essentially the auxiliary field equation, which is an identity between two numbers, to an operator identity. And what you can show is that the density matrix, a full many-body density matrix, which is defined by this, can now be written as d of phi, p of phi. This is the probability distribution we had before. And this is not really a density matrix because G is not Hermitian, so you have to be very careful, but it's a Gaussian operator which has this form, right? So you can, so why would you believe me for this? Well, you can believe me by, saying, okay, let's try this. Let's try this equation and calculate for any operator, for any equal time operator. I will calculate over d phi, p of phi, the trace of what I've given you here. This is this phi here times O. Then I will get essentially the operator, the same form as what I would obtain by using this form, and then by doing the Wick decomposition of the given operator I had before. So this is, I don't expect you to understand this as quickly as I said it, but this is an extremely nice equation. So in principle, it allows you to calculate many things. I mean, it's not always stable. It comes with some problems, but it gives you the possibility of calculating Renyi entropies. Francesco, which is also a member of our group, he also was able to calculate entanglement Hamiltonians with this, based on this ideas. So it's pretty powerful. And it's also a very elegant way of formulating the auxiliary field, Monte Carlo, in my opinion, right? So that, I think that's, for me, that's the most important equation. Good. So I will continue if there's no questions. Absence of sign problem. When do we have no sign problem? That's very important. Most of the absence of sign problem is based on symmetries, right? And so there's been a lot of progress in this domain for over the last years, and I'll give you the simplest possible argument for the absence of sign problem, and that's based on essentially on Kramer's theorem. We will assume that we have so that the question is the action real, right? And so we will assume that we have an anti-unitary operator with squares to -1. So what does that mean? T hat is an anti-unitary operator. That means that it can be written as U hat, that's a unitary operator, and K is the complex conjugation, okay? And we would like this operator to square to -1. And what we would also like is that this operator is a symmetry of the propagator T hat, right? So this T hat is a symmetry of the propagator U hat, right? So that these things commute. Then we can show that the weight here is always positive, is semi-positive, positive semi-definite. How do we do that? Well, there is, in principle, it's pretty easy. There are some details which are very important. Well, let me assume I have an eigenvector of U with eigenvalue lambda, right? So now, because T commutes with U, I can multiply on both sides here by T. And then because T is anti-unitary, right? Then if I commute my T and lambda, I get a lambda complex conjugate. So what does it mean is that if I have an eigenvalue lambda, then I have an other vector, T of the time reversal of nu, which has eigenvector lambda bar. So if I can now show that these two vectors, T of nu and nu, are linearly independent, orthogonal to each other, for example, then I'm done, because I'm sure that lambda and lambda bar, if ever I have an eigenvalue lambda, then I have eigenvalue lambda bar, multiply them, the determinant will always be bigger than 0. Now, how do I show that? That's where the point t squared is equal to -1 comes into play. If I have that t squared is equal to -1, then I can show that t nu times nu, the scalar product, is equal to 0, meaning that this eigenvector, this vector here, is orthogonal to this one, right? So one can show this, and we can show this in more detail during another session if one asks the question. What is very important to show, to see, is that when you want to do the calculation here, you will have to assume that the T on the vacuum stays the vacuum. So you have to have some type of particle number or U1 type symmetry to enforce this, right? So that is something you will need if you want to prove this up to the last epsilon. An example of this would be time reversal symmetry. So time reversal symmetry for spin 1/2 tells me that the up electron goes to minus the down electron goes to the up electron. This is antilinear, so if I have an alpha here, so if I put in an alpha here, anti-unitary, then I would have an alpha bar here, right? That would be nice. Good, so I will give you this. This is Kramer's theorem, essentially, and it was pointed out by Susheng Tsang and Kongju Wu some time ago, that we can use this theorem essentially to show the absence of sign problem. There's been, before I go continue, let me show how to use this for our case. That's maybe more interesting. So how do I use this theorem to show that this action is always positive? And the easiest way to do it is going into 2 steps, right? The first step is I'll do a canonical transformation, which is a partial particle hole symmetry. And that's where the question of bipartite comes into play. I will assume, so for the spin up goes to the spin up, the spin down goes to, so the C dagger, the particle down goes to the hole down with a -1 to the I. -1 to the I is just a shorthand notation to give you, this will be, if I will separate my lattice into an A sublattice and a B sublattice, and -1 to the I will be equal to 1 on sublattice and -1 on the other sublattice B. And what I would need is that I do the canonical transformation, and the hopping will remain invariant, provided that, there's a J here, the hopping will remain invariant. So that was the question we had before. The hopping H0 will remain invariant under this transformation, provided that I and J link only between sites of the different sublattices. Because if they do this, then I will get, because of the canonical transformation, let's say for the spin down, here I will get a C of I, C dagger of J, but because I and J are between a different sublattices, I will get an extra -1, which I will get rid of by doing the commutation between C of J and C of I, right? And T, of course, is a Hermitian matrix, right? It's a hopping. So what is very important is that, let me answer to Florian. Yes. So this is important. H0 is invariant only if I have hopping between different sublattices. That means no chemical potential. So if we do that, then this E of minus delta tau, this goes to this density here goes to the Z component of the spin. Okay. So now when I have written it down in this formulation, then you see that this is really, that it's fairly straightforward to see that this is invariant under time reversal symmetry. Because, so now if I do t hat t minus 1 here, essentially what you're seeing is that time reversal symmetry does not change my H0. Okay, so, or it can't change it, but okay, no, it won't change my H0. And this SZ goes to minus SZ, but because I have an I here, the minus I get with the SZ going to minus SZ compensates the minus I which I have here because T is anti-unitary. So basically this, what I'm telling you is that this remains here invariant. So using this transformation, you will see that this code for the long-range Coulomb, if you define it in this way for these type of hopping Hamiltonians, then you will see that it is invariant, it has no sign problem. So I told you that there has been a lot of progress in the sign problem, and this is a list of, well, not so recent anymore, but articles which are extremely useful to show if there is a sign problem or not, essentially based on symmetries. And so maybe the most general way of doing it is to going to a Majorana basis, to Majorana fermions, and you ask yourself the question here: if I give you a number of A1 to AN skew-symmetric matrices, then what is the condition on these matrices A1 to AN such that the trace over this Majorana version of the propagation we have been talking about is always bigger or equal to 0? And for example, in this article here, they have introduced what they call Majorana time reversal symmetries to be able to show this in a very pretty straightforward way. Okay, so there are symmetries. The point of this is that you should only use symmetries to be able to show, in principle, before you start simulating, that there is no sign problem. If you find a sign problem and you don't expect one, or you have a bug in your calculation, or you have a bug in your program. Okay. Let me now go on, see where we are at. I can finish with this slide. And essentially, before taking questions and going on tomorrow, essentially now you can, so this is the slide I was showing you about a general spin model coupled with a spin model fermion with this special Kondo type coupling between the spins and the fermions. And then you should be now able to see pretty quickly that there is actually no sign problem, because we always have essentially squares, right? Squares here of terms where, first of all it's a sum of squared terms. These are all squared terms. What comes in front is a positive, something always positive. That's why we wrote down some absolute values with a minus in front. So this minus is very important. And everything here inside the square is time reversal symmetric. So you will be able to show very quickly, essentially, that there is no sign problem for this general Hamiltonian. Once you wrote it, once you understand that you can write it in this way, and you see that you always have perfect squares with prefactors which are always negative, and what's inside the perfect square has some time reversal symmetry. Okay, so that's a bit quick, but essentially you can train your eye to see pretty quickly that there is no sign problem. Good. I'll finish on this note. What do we do if there's a sign problem, and why is a sign problem bad? So let's assume that S is complex. So I can't use this to sample the Monte Carlo. What I will do is introduce some type of a reweighting scheme. I'll take the absolute value here, and I will essentially sample this. Now to sample this, I have to normalize it. So I divide by this object here, and I have to also take into account the partition function. The partition function, that is essentially the absolute value of S times the phase, right? So this is the phase here of S. And I have to divide, because this and this will basically disappear, will cancel. And so I have to divide again by this. So you see that I can recast my object here, with a sign problem, to the quotient of two different objects which I can sample with Monte Carlo. And this is what you call the average sign. And this is the observable reweighted by the average sign. And the probability I will sample is this. I will sample this probability distribution. So why is this bad? Or why is there a problem with this? Well, the problem is the average sign. You can argue, you can show in specific cases, that the average sign is actually the quotient between two partition functions, where one has a fermionic energy and the other one has, in case of word lines, you can really show it for some examples, as I said, that this would be the partition function for the same problem, but with the fermions replaced by bosons. And so if the quotient of those two partition function is something which scales as e to the minus beta, the volume times something extensive. And so this will scale as e to the minus beta, maybe the fermionic ground state energy per site, minus the bosonic ground state energy per site. Normally, the bosonic ground state energy is lower, so you will have an e minus beta n times delta, and delta is a positive small number. So that's in principle no problem. The problem is that if I want to divide by this positive small number, then I have to be sure that the uncertainty on this positive small number is smaller than the number itself, right? But as I told you at the beginning, the error scales as 1 over the square root of the CPU time. And since z over z bar scales exponentially to 0, that will lead to the fact that the CPU time has to be bigger than e to the 2 beta v times delta. And so you have, because you're dividing by something which is very small, you have to pay an exponential computational price to be able to keep the precision as a function of inverse temperature and volume, okay? That doesn't mean that we cannot access high temperature physics. We can still work with sign problem. We can do a lot of interesting things with sign problem, but you will always be limited. It stays an NP hard problem. Many things which are important, delta is method dependent, delta is Hubbard-Statonovich. It depends on the choice of the Hubbard-Statonovich decomposition, et cetera, et cetera. There are many things for which delta, so you can maybe find a formulation. Well, delta is very small and solve a problem, practically solve a problem where you have a sign problem. So this is the last slide I have for today. This is the average sign for a Hubbard model on a 6x6 lattice at U over t equals 4. And you see that, well, this is half filling, this is finite doping, right? So the finite doping, this is where the high TCs are, for example. This is the average sign here is too small to do anything. You have a complicated form. These are filled shell configurations, etc. So but invariably, if you want, as a function of inverse temperature, it goes down to 0 exponentially, and everything becomes exponentially expensive. Just let me finish on a positive comment. You see, what's important is our scales, right? If you take the Hubbard model at U over t equals 4, I just happen to know that the effective magnetic scale is of the order of 0.25t. So it's pretty high, right? So it's beta equals 4. So beta equals 4 gives you the magnetic scale. So if you cool your system below 0.25t, temperature below 0.25t, you start to see short range magnetic fluctuations. And you see that we can go to beta equals 6 or 8, something like that, beta 10, maybe not, beta equals 6 or 8. So you see already when you cool your system to beta equals 10, you already see the physics. So beta equals 10, that's basically a temperature kVt of 0.1. So I'm a bit ambitious, so it's maybe 0.125 for 8. And then you see that you're factor 2 smaller than the J scale. So you see a lot of very interesting physics of local moments interacting with itinerant, with electrons. And that has, helped us a lot to understand motions of, basically motions of holes in state where you have short range magnetic fluctuations. So my point is that you can still do something with the sign problem, but compared to the cases where you don't have a sign problem, you are limited by this exponential factor. Okay, so I will stop here and continue tomorrow and take questions.
Thank you, Fakher. Are there any questions in the audience? Arun Grover has a question, it seems.
Yeah, I had a question, Fakher. Hi.
Yeah.
About the sign, the previous slide.
Yes.
There's a hump at 0.7. There's a small peak at 0.7. Do you know why?
Yes, it's a filled shell configuration. So it happens that if you go at this filling, right? If you take a 6x6, basically it's the non-interacting ground state is a non-degenerate.
Okay, I understand. Okay, yeah. Okay.
So you can. There's been some attempts. So these humps are of course dependent on if you take tilted lattices or different geometries. And so you can try your luck and play with it. It becomes a bit chemistry to them, right? So you have to find the correct lattice which you want, which optimize the sign problem for the simulation, the doping you want.
But it's not a feature of thermodynamic limit. It's nothing is special.
This is all weak coupling. This is also this is U over T equals 4. If you go to stronger coupling, this hump disappears a bit.
Okay, good.
Okay. That's
Thank you.
Thank you. Any other questions? Do you want to say anything about the method dependence of the sign problem? You just
well, if you the method dependence. So that's a big question. Generically, if you use word line type methods like word line, SSE, or you have a sign problem, then it will be worse than if you can formulate things with the auxiliary field. That's my point of view. So, for example, if you take free electrons in 2D and you try to simulate this with a word line type approach, then you will have a dreadful sign problem and you'll be dead. If you do that in real time. If you do the auxiliary field, because you solve the problem exactly, essentially you have no sign problem, et cetera, et cetera. So the auxiliary field is one of these approaches where the sign problem is maybe the best. So I'm sure there's an exception to this statement, but you can at least argue this. And then there's another dependence, which is the dependence of the Hubbard-Statonovich transformation. If you can produce this, right, by using this type of perfect squared, right, where essentially if you take this and you do a Hubbard-Statonovich decoupling, then the field will couple to the z component of the magnetization. And you get a better sign. If you use another Hubbard-Statonovich decomposition where you say, okay, I'm going to write my Hubbard U as U times Ni up plus Ni down minus 1 to the square. That's perfectly legal. And then you do a Hubbard-Statonovich because this is positive, and you will get a code which is complex. And believe me, if you take beta equals 2, you just do it this way. If you take beta equals 2, the sign will be basically 0, right? So you can play a lot with the sign, with the formulation, auxiliary field, or word line, or something else. And then within the auxiliary field, you can optimize the sign by choosing the correct Hubbard-Statonovich. I could go on. If you take this case, right? If you take this case, then you can show that the imaginary part of the action is basically pi, right? Or pi or 2 pi. Pi or 2 pi. So the sign, the imaginary part of the action is basically fixed to pi to minus 1 or 1. The imaginary part of the action is fixed to a phase. You have many more fluctuations, and it turns out that's heuristics. It turns out that it's much harder to control this, and you have a much worse sign problem. And if you're able to fix the imaginary part of the sign to pi or 2 pi, right? So you can.
There's another question by Inyabanta Swain. He has raised his hand. So if you speak up.
Yeah, hi. I have one question, which actually in this slide itself you mentioned, like also when you are describing how we decompose into the Hubbard-Statonovich fields.
Right.
So you suggested, like, let's say if I have the repulsive Hubbard, either I decompose it down, let's say the magnetic channel, or even the, let's say the charge one. But like the Hubbard model in a sense has the physics of both the charge and the spin. So is it like always recommended to kind of decompose into either of the one, or is it possible to have like both the?
You can do a mixture of the both. There's no problem. You see because this is an exact method. Ultimately, the result will not depend on the channel you use, right?
Okay.
Right. So if you decompose in the charge channel by using, so the charge channel will be this, right?
Yeah. Density, yes.
So if you take this, then you do see the same result. You can test this. You can test this during the week, right? What you could also do, which may have some advantages in different contexts, is you can combine them, right? You could have an alpha basically, and then 1/2, and then Ni up minus ni down squared plus 1 minus alpha, right?
Yes.
And then the other, that would be then the charge, and then here you would have basically a 1/2 ni up plus ni down minus 1 squared, right? That would be a possibility. You could program this and show that your result should be alpha independent, and they will be alpha independent unless there's a bug. There's one thing which is I think more interesting in the choice of the Hubbard Statonovich. If you take the charge channel, right? If you take the charge channel, then the field will couple to something which is SU2 symmetric, right?
Yes.
Right? So you have SU2 symmetry built in, right? So SU2 symmetry is present for every field configuration, and that is sometimes very useful, right? Because it's very hard to restore the symmetry. So what could, for example, happen, and I really suggest to try this week. Take this field configuration, take this, right? Ni up minus ni down squared, right? And then you do, so of course the field couples now to the magnetization. And so you, of course, break the SU2 spin symmetry down to a U1 symmetry. But of course, because this is exact, this has to come back to the correct state, to the right result. So essentially, if you measure the ZZ correlation functions between ij, that should be equal to, let's say, the x between the x and the y. So if you are at high temperatures or far from a critical point or not in an ordered state, then this is very easy to do. But if you are close to a critical point or in an ordered state, then it is extremely hard to get good enough sampling to restore the symmetry. Is that okay? So in this case, you will have to, define, we will talk about this later, an improved estimator to be able to restore the symmetry. But it is one of the differences, if you want, between the two choices of Hubbard.
That's okay.
Yes.
Here you were implicitly assuming that you're looking at the repulsive interaction case where spin is the relevant symmetry breaking channel for this restoration of SU2 symmetry.
Sure. I was saying that if you're close to a critical point, I was meaning magnetic critical point.
Yeah.
That's what I right. Yeah.
And in the attractive interaction, it would be, the image would be inverted. You would maybe prefer to use the spin decomposition because of the same reason if you found charge density wave and similar things.
Okay.
I had one more question.
Yeah.
Maybe,
Go ahead, Tom.
about the, so if so the problems which have actual boson, not rotors, or like real boson which can take any occupation from 0 to infinity, they're generally very hard. At least, I don't know, they seem a bit hard in normal Monte Carlo, like SSC, I thought. And is there I would think they also have some kind of a similar formulation, I would think, some determinantal version, because integration of bosons and path integral also give determinants, at least within.
Yeah.
So have people used for doing not hardcore bosons or spins, but real bosons, have people used similar techniques to, I remember there's some paper I was told by Doug. I don't know.
There were some papers by a person called, there were some papers, I don't have it in mind. There were some papers, but I would have to look through them again. But they were interested to do auxiliary field type for bosons.
Right, I see.
Or Southcore boson, as you say. That's a question, Taro.
Okay.
And,
yeah. So
okay. I can find the name of the person and I look at the paper again. I don't have a good answer. So the question is it better than doing SSE, for example? Right.
And SSE is not. I thought that it's not that easy for real bosons. I thought if they're hardcore bosons, SSE works very well. But for real bosons, I thought it's a bit harder. I'm not expert in SSE, but maybe you have something to say.
I can't answer the question for the bosons because I haven't studied it well enough to be able to answer the bosonic. I mean, I know that what was his name? He was a Belgian person, was doing this was trying to formulate the Lorentz for bosons. Laurent Paulier was also doing this during his PhD thesis some time ago.
I see.
And was not, and I mean, these are just conversations, was not so, seemed to be not so easy, but I would have to go back and look at the paper.
Okay. Okay. Yeah, maybe we can find the paper later. And yeah, thank you. Yeah.
Thank you. I have 3 more questions in the queue, basically, and the next one would be by Bo Xiao.
Yeah.
Yeah. Can I ask you a question about it? Because you use the Trotter decomposition.
Yes.
And if you do this in non-symmetric way, symmetric way, and you see the dips in the Green's function, could you please explain this dip a little bit more?
Yeah, it's basically you have a Hamiltonian. Essentially you get an imaginary part, right? Your energy normally is a real quantity, right?
Yes.
But if you do the asymmetric, then you will get basically an I, and then a small imaginary part to your energy.
Mm-hmm. Yeah.
So that's the whole thing, right? So that's basically if you take this propagation here, right? This object is not Hermitian because H1 and H2 don't commute with each other, right? So if you do the calculation, that's equal to e to the minus H3. H3 is essentially H1 plus H2 plus, correction term, and H4 is proportional to the commutator of H1 and H2. So now, what happens is that if I calculate this, then I will have factors E of minus tau times the energy, correct?
Mm-hmm. Yes.
Then the energy becomes something like this, but then I have to replace this by an imaginary part, and then you see that you will have oscillations.
Okay. So
sorry, this is the absolute value, right? Because I'm plotting on a log scale. It's a small effect, right? I mean, this is 1, 2, 3 orders of magnitude, right? So it can be, you can say it's a small effect, but sometimes it's really a pain. And so these are basically the zeros, right? This is the 0. I have an oscillation here, and then it defines a 0, and that's where the dip comes in. 0 goes to minus infinity.
okay, so if I look at this graph, the tau equal to 0, right? That is the equal time Green's function.
Yes.
And so if you use this in there's a non-symmetric decomposition, but for the equal time, you get some observables which you just use the equal time Green's function. You get just like the density or whatever. So you are not going to see the effect of this dip.
No, we only suffered from this for the imaginary time.
Okay, so if you get some non-equal time measurements like susceptibility, right? You get the parent susceptibility, you might see these dips.
Yes, you might see these dips. You should check, right? It depends on there's no, I'm not telling you that it could be that this is 0, right? I haven't told you that this is always non-zero, but you just have to check. What is very painful, Bo, is that if you try to put in this type of, very often you calculate these objects to be able to do an analytical continuation, right? Real frequencies. And if you put this type of data in the analytical continuation, it just crashes. Right? So this is very painful. And it's a big, you break hermeticity of the propagator as symmetry, so that's bad.
Okay, yeah, I see the reasons. Yeah.
Thank you. But you can live with it, right? I mean, you can live with it.
So the next question, as far as I remember, was by Joel Hutchinson, but in the meantime he has lowered his hand. Do you still have a question? It seems that is not.
No, it's okay. Thank you.
Okay, it's okay then. So then the last question by Eduardo Ibarra Garcia Padilla.
Oh, hi. I do have a question about non-ergodicities in the Monte Carlo.
Yes.
So, when you're doing a simulation, you fight both the sign problem and like sticking.
Yes.
So, of course, you want to pick your Hubbard-Statonovich transformation to have like some symmetries, like for example, what you were previously discussing about the SU2.
Yes.
But do you have any insight of like how of a good way of reducing this sticking issues depending on which Hubbard-Statonovich transformation you pick?
So the sticking issues, you mean, for example, an attractive Hubbard model at large U?
Yeah. For example.
No, I don't have a. No, the answer is no. right? This is a very hard question. To be honest, when we have ergodicity issues or sampling issues, then we try to look at different updates. We try to look at global updates, but it's extremely hard to choose the global updates. So once you formulated an auxiliary field and you start to run and you see that you have long autocorrelation times, etc., then the truth is that it's a hard thing to try to solve it. So I don't have a good idea of how to do that. So, but we play around. I mean, the ALF code, I think this is one of the big challenges, right? You can get rid of the sign problem, but then you have the long autocorrelation time. So the ALF, we spent a lot of effort to have put in parallel tempering. This may help, may not help. Or you can try to do, we have a routine to do global updates, both in space and time and only in time, and only in space. And you can try your luck and try to define global updates which will circumvent these long autocorrelation times. But because the action is non-local, it's normally rather hard to devise these moves, right? So that the acceptance stays good.
Can I add a comment?
Of course.
To this? So I think in general, this is perfectly true that it's extremely hard to overcome autocorrelation issues. But in this specific example of attractive Hubbard interaction, wouldn't the MC decoupling help when you expect that a charge density wave or a superconductor is an instability at strong attractive interaction? You change the opposite physical sector for your auxiliary field to encode the symmetry.
You generate a sign problem if you dope it, right?
Okay, if you dope it, yes. But at half filling, it would work.
At half filling, it will work. But the question was, I think, I mean, yeah. So if you dope it, you don't have the choice anymore. You generate the sign. You're stuck with the.
Okay, that's.
It's a hard question, right? We should collectively think about this and try to develop better updates. Let me just add this, Florian. A big part of what we're trying, Langevin global updates with Langevin hybrid Monte Carlo. These are attempts, at least, to get better sampling. It comes with a set of problems, but this is being built into the code so that one can try his luck with different types of updates.
Awesome. Thank you.
You're welcome.
So then I think we can close this part of the workshop. So if there are no more questions by the audience, because practically speaking, the next session starts in about 10 minutes. So we get 10 minutes of break. So let's thank Fakher again for answering questions and his nice introduction to ALF. And we meet again at 13 minutes for the introduction by Jefferson with the introduction into ALF. So we are still around. If you have questions, you can. The Zoom session stays open. You can ask us questions. Maybe we are not entirely in the office for the next 10 minutes, but we will be around in this Zoom room definitely. So thank you all.
Okay, can I just ask maybe to Professor Assaad just one thing?
Yes, go ahead. Yeah.
So you discussed about this equal time, let's say, observables like green function or like that.
Yeah.
But let's say, will you be discussing something about this non-equal time ones, like let's say to measure current and like those things?
Exactly. Yes.
Oh, okay, I see.
So what was the question? I didn't get that. I'm sorry.
No, I mean, is it like, within ALF also like to possible like to calculate this, say different time correlations and that one?
So yeah, so that's possible.
Oh, okay.
That we will. There are exercises on this. Yeah, of course.
Okay.
So the ALF comes in with the imaginary time displays correlation functions, which are calculated. And this ALF 2.0 also comes with a maximum entropy code that allows you to do the rotation to the Vic rotation.
I see. Okay, thanks.
You're welcome.
Can I ask you one question about the autocorrelation time?
Yes, with pleasure.
Okay, so let's just talk about this Hubbard model, right? You just like you just had hopping terms and you had this local interaction, right? What is do you have a analytical equations for this autocorrelation time as a function of these parameters?
No, I don't have an analytical expression, but in the documentation there is an example, and the autocorrelation time can be calculated within the ALF, right? So there's an example on the error analysis for autocorrelation times. I think that was for the repulsive Hubbard model, or different for the spin correlations, the z direction, x and y directions. You will see that they are not so long for the parameters we chose, but I don't have an analytical expression for it. That's an extremely hard question.
Okay, yeah, I'm sorry. I see the point. You know, for different observables, you should have different autocorrelation. Exactly. But let's say if we have an electron phonon model, right? We get this omega, because this electron phonon model always suffers from long autocorrelation time, because you get this continuous field, which is x displacement of the phonons. Let's say if, but I think in some papers, I don't remember this clearly, but I think in some papers they said the autocorrelation time for the electron phonon models, which depends on some functions of 1 over omega, which omega is the frequency of phonons. Is this correct? Or
so it's correct that you see when the phonon. So okay. So the question has many parts, many answers, right? So if you're talking about the autocorrelation time for single spin flip updates, correct?
For this one, it's not a. Let's just focus on the electron phonon models. So there's no spin flip.
The question is, if I talk about autocorrelation time, I also have to tell you what type of updates I do.
Mm-hmm.
Right? So, so if you have local updates, right? Assume that you can formulate the Hubbard-Holstein model with local updates within the auxiliary field that you may know, right? And then I can go up and do some local updates. If I do some local updates, then of course the autocorrelation time should become bigger when omega 0 gets smaller, right? Because you agree that when omega 0, the phonon frequency gets smaller, then the extent in imaginary time where the field is constant gets bigger and bigger.
Mm-hmm. Yes.
Right. And so you have a scale which is 1 over omega 0, which is the extent in imaginary time where the field is more or less sort of like constant. And then you do your local updates on a time scale which is delta tau.
Mm-hmm. Yes.
And so you have a mismatch of energy scales, right? You do your spin flip, or you do basically your local update on a very high energy, and it's very hard to sample the long wavelength in imaginary time, dynamics of the phonon. I think that's the problem.
Okay. Yeah.
I mean, do you have experience in this or not?
Yes, I have experience, but not that bad. Yes, because we have some experience about this electron phonon models. So the question is how small the omega can be, right? We in the literature we just use 0.5 or 1.0. This is very common, but can we do better? Because the omega is too large for a real material, right? We go to this.
So this is we should talk about this in private, but in principle you can try your luck with different type of sampling schemes in the small omega 0 limit. They may be more efficient, in my opinion.
Yes, we tried this local update. For phonon field, it's just like an XY model, right? You just displacement change this X,
right.
But a little bit. We tried this local update and a global update. We try both of them, but still we want to know what is the limit of this.
You could try Langevin dynamics, right? You can have different type of. You can try different dynamics and see what. That's a possibility.
Yeah, I think Langevin is also one research direction. Yes, yeah. But we can talk about this maybe later. Yeah.
Yes, we can talk about this later. But in principle, that could be possible.
Okay. Yeah.
Okay.
Thank you so much.